So next one, let's make this situation more complicated. And on purpose, in order to move to the next problem, first I decided to discuss two wires, right? In order to get the strategy of the problem. And now let's make the situation more complicated. And this is also your homework. In your homework, we're going to solve only part A, but in your homework, you're going to solve part A. You're going to have part A, B, and C, 3 parts. But the idea is very similar. So in this problem 2936, we will have 3 parallel wires with currents, but currents can be some of them in the same direction, some of them in the opposite direction, but 3 wires. So we increase complexity, so we're adding additional wire. But of course, this strategy will be very similar. Again, you will have to make a decision which object experiences the force. And in all parts, in part A and B and C, that object is going to be different. And also, you need to make a decision which objects are your bullies, right? Which exert forces on your victim, right? Okay, so now let me erase this part. So that's, as I said, problem 2936, and it will be part A. And now wires are positioned horizontally, right? So let me draw them. So the first one I will use, black. I'm trying to estimate the amount of space that I might need. So the first wire, current this way, I1. Then the second one, let me use blue color. All right. Current opposite to the first one, so this is I2. And the last one will be here. And current the same as the first, I3. So all these currents are of the same value. All right, so let me write here I1 equals to I2 equals to I3 equals to 10 amps. But of course, I will use subscripts properly. I know that you guys like to start using immediately numbers. No, I'm going to use I1, I2, I3 because we need to have a clear picture which current we use in this role or that role. Right? Then some geometry is given. Distances between these wires. Okay, I will probably draw it here. So let's say this is A and this is B. Although they are the same, I still use different symbols because we need to have a clear understanding which distance is used over here or over there, right? So if you just use numbers, you will lose track of where what's the contribution of that distance or this distance in the final result. Right. So A is equals to B equals to, what's the number? 20 centimeters. So I convert it to meters. No, 2 centimeters. Sorry, 2 centimeters. 2 times 10 to the power of negative 2 meters. Right. And so that's what is given. And now, another thing that we will need in order to get through the calculations. Let's assume that this length is given. It's sort of like similar to this, although we know we have infinitely long straight wires. But let's solve it assuming that length is given. And then at the end, of course, you can, all the time, you can introduce the force per unit length. Right? Because, yeah, lots of similarities between these two problems, except for now we have a more complicated situation of 3 wires. So now the question, what needs to be found? Force which way I label it? F1 probably. No, I just labeled it as, no, F1. Yeah. So let's write let's find F1, which is basically the net force on I1. And now you should be able to guess what are the questions in part B and part C. In part B, in your homework, you will have to repeat steps, but you will have to find similar steps. But you will have to find the net force acting on the second wire. And in part C, you'll have to find the net force acting on the wire I3. But here we're going to find the force on I1. And again, before we start discussing, we need to again sort of divide these objects into victims and bullies, right? So into the object which experiences the force and objects which exert forces, right? So from the question, since we want to find the force acting on F1, so that is our victim. That is the object which is going to experience forces. But of course, now the force is going to come from two places, right? There will be two punches, right? At the same time. So the first one from the blue and then from the green. Right? So, so this will be our first object which is going to exert a force on I1, and this will be the second object. Two bullies against one victim. It's not fair, but quite common. Right. So now let me write what I just told you, because yeah, I think that's one of the first things that you need to realize. So I2 and I3 sources of B1 and B3. So let me write this. I2 and I3 are sources of B2 and B3. So they're going to create their own magnetic fields. And then, of course, wire I1 is going to interact with these magnetic fields, experiencing the force. Right. And they exert, and they exert forces on what I'm writing on I1. But I'm going to find the net force in this way. I'm not going to calculate separately force from I2 and separately force from F3. I'm going to calculate the net field created by these two wires, and then, of course, that net field I will use to find the net magnetic force acting on on I1. Although, of course, both approaches are going to give you exactly the same result at the end, right? Of course, you can find first separately force that I2 exerts on I1. It will be very similar to this. Then force which I3 exerts on I1. And then, of course, you'll have two vectors, two forces. You just need to add them as vectors. But I decided to make slightly different approach. I want to find the net field, net electric field at the place of the wire I1. So basically, it will be B2 plus B3. And then use that net magnetic field to find the net magnetic force immediately. Right? So I use principle of superposition on the level of magnetic fields, or if you want, you can use principle of superposition on the level of forces. So it's up to you. So now let me write this B1 and B2 and B3. So B2, of course, it will be equal to mu naught times I2 divided by 2 pi. And again, we're interested in the magnetic fields where? At the place of the victim, at the place of the I1, right? So for the second wire, for this magnetic field, so of course, we need to use this distance A, right? So it will be divided by 2 pi A. 2 pi A. And direction, let me write over here next to this. Direction, how can we find direction? Right hand rule number 2, right? Outstretch your thumb in the direction of the current I2 and curl fingers. So above, okay, first let me show that, of course, we're going to have magnetic field lines like this, right? Circle. And directions like this, right? Let me check. Yeah. So it means that above blue wire, all the way to that infinity, we're going to have into crosses. Right, so let me draw a few, couple, yeah. All right, so will be cross, cross, and here I can draw cross, cross. So that's our B2. But below blue wire, of course, we're going to have dots, right? All the way to that infinity. I can draw it here, so it will be dot, dot, and here I can draw, it's a dot, dot. So that's again our B2. In your part B and C, you will need these dots and crosses. That's why I'm drawing them everywhere. Now the blue, I know, first I need to write the direction. At the point of I1, it will be into the board. Into the board. Right. So now let's do the same for B3. Magnetic field created at the level of wire I1, but now created by this green wire. So it will be again guys, again, if I'm trying to be as thorough as possible, but if still you're getting lost somewhere, right? Tell me. All right, if something not clear, if some my logical steps, okay, according to me, logical, right? Maybe they're not so logical. All right, so just tell me, right? If you need clarification. So mu naught I3 divided by 2 pi, and now the distance from the wire, green wire, to the point of wire I1, because we want to find the net magnetic field and eventually net force acting on I1. So now, of course, distance will be B plus A, right? B plus A. Probably I should have written A plus B, sounds better. I will change in the next line. Right, and direction, again, right-hand rule. So outstretch, right-hand rule number 2, right? Outstretch your thumb in the direction of the current, and your curl fingers are going to give you direction of this magnetic field line. So let me draw them here. Right, this. So, and it will be this way. Right, is that correct? Let me check. Yeah, that's the correct direction. So now again, I'm going to draw my crosses and dots. So below, into the board, into cross. So that's B3. Here again, cross. So all the way to this infinity, where you can draw as many crosses as you want. And of course, above this green wire, all the way to that infinity, we're going to have dots, because magnetic field, you see, B3 is out of the page, out of the board. So dot, dot. Here I can also draw dot, 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 and dot. So that's B3, and I can also show here it's a B3. Right. So direction at the place of the wire I1, direction of B3 out of the board. Again, as I said, you will need all these crosses and dots for your parts B and C. Right? And again, don't be afraid, because some students get confused. Don't be afraid to draw all these, for example, dots above this blue wire, because each of these wires, they create their own magnetic fields independently of the rest of the wires, all the way to that infinity and all the way to that infinity. Completely independent creations, right? So now, can you tell me which field is going to be stronger? Because now you see at the place of the wire I1, both of these fields are in opposite directions. B3 is out, B2 is in. So we need to make a decision. I just want to make a decision. Should I subtract B3 from B2 or B2 from B3? right? So that I will get the positive number at the end, right? I think for everyone it's obvious which field is stronger. Since source of B2 is closer, right, to these points, of course, so magnetic field B2 is going to be stronger. So this wire is farther away from wire I1, right? So of course, magnetic field at this level is B3 is going to be weaker, right? So let me use that fact, right? Which way I wrote it? I just wrote underneath. So B2, of course, is larger than B3. And which way? I justified, of course, at the place of the first wire. Or just a second. Right. At the place of the place of the this wire I1, but of course at different points, this is not going to be correct, right? So you have to be careful. Right. So let me add this at the place of the first wire, right? At the place of the first wire. Okay, so now let me write a net magnetic field, and then the rest of the problem I will finish after the break. All right, so I can write B net, right? And you see, I'm not writing a vector on top because it will be basically what I'm finding the absolute value. And then, of course, I will write in the bracket direction of this net magnetic field. Right. At this problem, I decided not to use coordinate system. Usually, you notice that every time I'm trying to introduce coordinate system before I start dealing with these vectors, but this time I decided to do it this way, which very often students prefer. So it will be, of course, B2 minus B3, because we just discussed that B2 is larger, right? And we can write which way. I will factor out mu naught divided by 2 pi, I guess, yeah. Mu naught divided by 2 pi, and we're going to have I2 divided by A minus I3 divided by A plus B. And direction, since B2 is stronger, of course, it will be into the page, into the board. Into. Okay, I'll just write into without writing into the board. Okay, so now we know the net magnetic field at the place of the wire of I1, and so what's left? Now we can start using this formula, because up to this point we just found this magnetic field. So net magnetic field, and the first wire is exposed to that net magnetic field. So just now I added 2 bullets sort of to separate. So pretty much in this first part, we worked with magnetic fields in order to find net magnetic field, and to which the first wire is exposed. And now we just need to find actually the net force. So in order to find force on the wire I1, it's a straight wire. Of course, we need to use that last formula, which we used already, once. So now it will be F1, right, because it acts on the wire number 1. And I. Again, which subscript do we have to use? It's like here, I told you at the very beginning. So this I and L, they describe that victim, which object which experiences the force, right? So in our case, it's a I1, right? So it's I1. So current I1, and then cross product of L and B net, right? And yeah, I wrote it as a vector, and we know everything about that vector. We know its magnitude, and we know its direction into the board, right? Okay, so probably, you know what, I should probably frame this quickly. So it's a preliminary result, right? Important. And of course now I will have to find direction of this force and then magnitude. Let's take care of the direction. L is determined by the direction of the current I1. So L that way. That's our first vector in the cross product. Then B net into the page. Into the page. So right hand rule. First align your hand along the first vector L, right? And again, you can position like this, like this, like that, but you need to orient next step like this, because only in this case you can bend your fingers in the direction of the vector B net, which is into the page. Into the page there, right? So you see my fingers, I bend my fingers into the page, into the board in the direction of B net, right? And L cross B, and you see my thumb gives me direction of this net force. So it will be up. So wire I1 is going to be pushed, right? Correct? Yeah. Right. So this will be direction of, where should I draw it? Probably I will draw it. I will draw a couple of vectors, so this will be F1, and also I can draw it here. F1, oh, I can draw as many as I want, but it should be enough. Right, so which way I wrote, yeah, first direction, so right hand rule number 1, it gives us that F1 is up, right? Again, you need to remember that direction of L is determined by the direction of the current, and then typical right hand rule. Again, guys, if you're still not comfortable with the right hand rule, come to the office. I waited yesterday, but no one came, right? Then magnitude. All right, so F1, now you see there is no vector sign on top. It means it's magnitude. So then I1 and absolute value of L crossed with B net. Right. So yeah, according to the right hand rule, so I1, then L absolute value, then absolute value of B net, and sine of angle between these two vectors, L and B. It's like here, right? You see, I'm almost repeating steps. And you can see on the picture, what's the angle between L and B net? B net is into the board. L is to the right, right? So the angle between them, L, which way? It's better like this, right? So L that way. B is into the board. You see, this is B. So the angle between them is 90 degrees, right? 90 degrees. So sine of 90 degrees. All right, so sine of 90 degrees is 1, exactly the same like over there. All right, so now I'll just need to grab my B net. It's this, right? And shove it in our expression. So now basically the final result. So it will be I1 times L, and our net magnetic field mu naught divided by 2 pi, and I2 divided by A, I'm just rewriting this, minus I3 divided by A plus B. I thought about making it look nicer, but pretty much it is as nice as it can be, right? Because yeah, you cannot do anything with this bracket, you cannot factor out anything, right? So that's basically the answer. Since numbers are actually given, A and B and currents are given, so of course you can calculate. All right, and I will just write down the answer. I'm not going to plug numbers. So it's a 2.5 times 10 to the power of -4. And again, it's just a force. Of course, the nature of this force is magnetic, but still just a force, so unit of newtons. And again, if you want, and quite often I told you people are interested in that value, you can introduce the force per unit length. So in that case, you just grab this L, and you know what I didn't give you? L, yeah, L is in the problem given, and I didn't give you that number. Without L, of course, you cannot solve it. Sorry. All right, so let me add here the top. L equals 50 centimeters, okay, 0.5 meters. Yeah. 0.5 meters. Okay. So now, yeah, now everything is given. Yeah, and direction, of course, up. So let me also add it underneath upward. So I will frame this whole thing because it's an algebraic expression plus number and direction.